Today's guest is Paul van Susante. He is an assistant professor in mechanical engineering and faculty advisor at Mining Innovation Enterprise. He has been involved in research projects for many customers, including Lockheed Martin, DARPA, NASA, the KSC, JPL, Bechtel, Caterpillar, NCHRP, the National Science Foundation, and others. I'm Felix Tuchinski, and this is Humanity and Beyond. So how are you doing today?
I'm doing good. It's been a crazy week, so it's been interesting with a power outage last night that screwed up my schedule, so it's been interesting.
All right, so let's jump right in. What got you into in situ resource utilization?
Well, as a kid, I was always really interested in space and science fiction and all kinds of cool things that we could do out there, cool planets where other, things may live and who knows what adventures. But, when I went to school, I figured out, hey, I got to do a bunch of stuff, got to work and make money and all those things. And those dreams come, of course, at a lot of hard work. And so when I went to college, the key there was that I was still interested in space, but I didn't really care for satellites or airplanes or something like that. And so aerospace engineering wasn't really what I wanted to do. So I ended up doing civil engineering. And the key there was that once I started to figure out a final project, I decided to do that on lunar base design and building telescopes on the moon. And that's really when I found out that, there is actually a role for a lot of other kind of disciplines in, space exploration than just aerospace engineering. And that's really when I started to realize, like, hey, even though I'm a civil engineer, I can still have a lot of contributions to make to this particular field that really, nobody's really developed yet. And so that's kind of how it all started, seriously, at least.
So it's interesting that we're kind of progressing from aerospace to civil engineering now as they're trying to build that moon base.
Well, exactly, right. And so when you have arrived at your destination, so when the flying piece is done, so to speak, that's when you have to start using the local materials, and so you're not just camping anymore, but you're also actually thriving and using the local materials to build new habitats and making your whatever you're trying to live, basically. So whether that's food or habitats or schools or anything else that you want to do, you got to make that using the local materials.
Of course, you know this better than I would. The Artemis program. I understand that they're trying to have a settlement that'll last for several weeks. Are there any plans there for in situ resource utilization? And there's probably experiments, but is there anything that they're going to try to produce, Is there any way to get few
For the Artemis program, you mean?
Yeah, for the Artemis program.
So in stages, right? And so like with everything, we have to learn how to do this. And so there is a planned schedule. And so there's Artemis missions every 2 years. So there's major, sort of call it major schedule, interesting things happening. And so 2028, I believe, is when they want to have an actual ISRU plant going, a pilot plant. Keep in mind that this is NASA, right? And so their goal is not to start settlements or anything like that. So that's not NASA's mandate. So they will build technologies and basic infrastructure to allow them to do the exploration and things that they want to do, but it's not their job to build a settlement, so to speak. If you want to go beyond, think maybe an Arctic type of research base, if that's what you want to do, then that's not really NASA's mandate. And so NASA is interested in technology and ISRU. So in this case, rocket propellant production, maybe landing pads, that sort of thing, at the scale and at the type of technology needed to do it at sort of an Antarctic research style base, if you will. Right, so that's kind of what NASA is looking for. And what they're looking for is that after 2028, when NASA has demonstrated the technology and they've basically said, we've now brought the risk down where we can count on the rocket propellant being available for our missions, they might want to hand that off to the commercial industry to then produce it for NASA, but also for any other economic purposes that they may come up with.
And that's where the construction of homes and schools and all that begins. Once there's a guaranteed fuel to return, I should say.
Well, homes and schools are going to be a lot longer, I think.
Mm-hmm.
So it's going to be research based for quite a while longer, because once you can make rocket propellant, you're not quite ready to build structures and things like that. So it's one thing to build, let's say, a berm or a heap of dirt or something like that that you sort of shield under, but being able to make a I don't know, metal or ceramic or some other type of material of a high enough quality that you were going to bet your life on it to live in it so it doesn't break or whatever, that's going to be a little while longer before we can do that. So we're going to have to research that a little bit more.
Gotcha. And how much will robots play into that? Like doing it remotely, like on the moon, of course, it's easy because it's a 4 second, well, not even a 3 second delay. Because a big concern, of course, is radiation poisoning, and you don't want people to be building the habitats and then for a coronal mass ejection to happen before they're ready and to get a giant dose of radiation.
Yeah, no, so robots are going to be an integral role in this whole thing. First of all, when we send humans there, of course, that will be very expensive to send a human there. And so I always joke, we should just send an astronaut with a shovel. It's much easier than designing a robot that can do it. But if you calculate how much it would cost per shovel, that would be very expensive, right? And so having a robot there that can do this in, a year, even though it goes pretty slowly, would be perfectly fine. And so the robots are going to play a huge role in doing these kinds of things. In a way, you want the robots to do the automated things, the boring things, the things that are sort of easy to automate. And you want the humans to do the complicated part that you actually have to think about, the problem solving, interpretation of data, finding like the interesting rock to pick up, that sort of thing. And the robots are doing sort of the boring stuff, the going back and forth, and then the excavating and the dumping, and doing that 100,000 times, right? So there's plenty of work for robots and for humans together.
Right, because I was thinking that the cost to getting a human and the cost of increasing the hab capacity of one more person, and all that person does is essentially something that could be automated. For that, it seems like it'd be cheaper in the long run than to have the equivalent of a delivery boy instead of just bringing another scientist up and having 10 robots do that job.
Yeah, so the question is, what are humans good at, and why do you want them there? And what are the robots good at, and why you want them there? And it's going to be a collaboration between the two, right? So if you think about maintenance, for instance, that's going to be pretty hard to do by other robots. It's not impossible, but you have to really design your robots to allow that to happen. And particularly in the beginning, when we're still learning how to do all these things, humans are going to be crucial in troubleshooting and fixing things and making sure that, if things don't go according to plan, that they can improvise and figure out what needs to be done. And so that's what humans are very good at. But the robots can do all the dangerous outside work, basically, right? So they can also allow the humans to sort of only go outside when they have to go outside.
Right. So what would you say is the most dangerous challenge? Maybe that one, like, or maybe not dangerous, but the hardest to overcome. Like, is it the fuel production? Is it? I mean, there is helium-3 on the moon, but can that be used? Is there any way to get rocket propellant, or is it just designing the robots to be able to do those automated tasks? Is that a difficult challenge of overcoming, or is it something else entirely?
Well, I think your question may be a little bit too broad here. So, are you talking about the biggest technical challenge?
Let's target that one first. So technically, in terms of technology that is required that still needs to be developed, what would be the most challenging task that still needs to be developed before we can I have a colony of sorts that is at least 90% self-sustaining?
Yeah, settlements require a lot of things, right? Before they would be self-sustaining. And so if you're going to make everything there, you're going to need a lot of things that you need to be able to make. So you need to be able to have metals, plastics, electronics maybe still need to be imported from Earth. That could be part of the 10%. Everything else, things like fertilizer, maybe water for, of course, propellant. That's one of the first things. And water is fairly easy to do. But then when you think about metals, that's going to be pretty tricky. They're sort of a byproduct. But once you have a metal, you don't have anything useful yet, right? So then you
Right.
still need to be able to process that somehow to either make it into sort of like a powder you could then 3D print and use for a 3D printer, or sort of more advanced methods like casting or other types of machining methodologies to make whatever you need to make. Um, and to me, one of the biggest challenges is going to be quality control. Um, so that you can make something at a small scale um, doesn't mean that it scales up well. Um, like if I make a pressure vessel, I only need one weak spot for it to crack, basically, right? And
Right.
so I can do it well for 95% of the whole thing, but that's not going to be good enough. And so the quality control of that whole process, the quality control of the material feedstock, I think is going to be a major issue before we can get to any kind of at large scale production of those kinds of things like settlements, like habitats or anything like that.
It sounds like we're almost redoing the Industrial Revolution, only on the surface of the moon this time. Because you have to get fine machine tools, and in order to have the fine machine tools, you have to have that whole regressive algorithm, I suppose.
Yeah, well, I mean, it's amazing if you think about, we can just go to, Home Depot or wherever and just buy whatever we need, or I just go to internet and I do that. If you think about the whole supply chain from the mining to the processing to the manufacturing to the transportation, and of course then to also the other kind of infrastructure you need in the house, such as power and light and water and other kinds of things, it's pretty amazing to see what kind of um, infrastructure really you kind of need to have before you can do all these kinds of things. It's not on the moon. You can't just go to Home Depot and say, "Hey, I want some tiles for my house that I'm trying to build." Right. So, how do you make those?
Mm-hmm.
Right. You can get some lunar regolith and sinter them or bake them, or all sorts of methodologies are possible. But what are you going to do? How are you going to do that? And tiles, of course, are not as crucial to be correct. Yeah, if there's a crack, oh well, it doesn't look so nice, but you didn't die because
Right.
the air escaped through it. So, there's certain pieces of infrastructure that have to have a super high quality when you deal with space, because you have no buffer zone. Like here in my house, if my window would break, oh well, it might be cold for a day until somebody comes to replace the window. But if on the moon my habitat would crack, and I wouldn't be there to tell the story. So you have no buffer there.
Huh. Yeah, it seems like the only way to do it would be to have multiple redundant systems. And that, of course, impacts the cost. It's a difficult challenge, I should say. So
Yeah, but I think we can learn those methodologies, right? So if once we figure out how to properly do that processing and get the right sort of feedstock of the material, so it's pure enough that I get a high quality product of material in the end, then I think we can do that. But it's going to take us some time to figure out, tweak the system, if you will, to make sure that we find all the failure modes before we would bet our lives on living in such a habitat that we created.
is that challenge? So is it that process, that supply chain challenge, hold true for going now to Mars, for example? So because that's a 2 year now instead of a 1 week in the case of emergency, it's anywhere between 7 months to 2.5 years.
Yeah, that's a whole different order of magnitude of challenge there for several reasons. Um, so I think there are some other challenges there. For like you said, the travel time is much longer. So um, the stability of food, for instance, so the nutritious value of food and keeping it for that long is an issue. So we may have to find a way to grow our food along the along the trip, basically, which we do not have to do when we go to the moon. Now, of course, we can practice such things on the moon, so we can figure out how to do these kinds of things. But I think there's some other challenges. Like I said, the trip timeline, and so if there are any medical emergencies or any other kinds of emergencies, the social aspects start to play a much bigger role when you have that sort of timelines compared to the moon. I mean, you can almost go to for like say a long trip, 2 weeks or so to the moon, but for Mars, you're talking multiple years.
Well, I mean, I heard they grew cabbages on the International Space Station a couple of years ago. So,
Right, right, and they're growing lettuce and I think radishes. They grew wheat, I believe, too. So they're looking at a whole bunch of different uh, things to grow that could help. But you need a lot of area to feed one person, especially for that long of a time. And so at the International Space Station, those were, of course, experiments to figure out, how they would grow under those kinds of conditions and which light would work best and all that stuff. So from a research perspective, it was very successful, but being able to do it at scale again, right? So it's hard to scale it up to a level where you can again bet your life on it because that's what you're doing.
right.
And that's a challenge. I don't think we figured out all of those things. We're on the way. We're doing the research, but we're not quite there yet.
Would you advocate for, in terms of the nutrition, a farm with like animals and everything, for before like a settlement can be established, or would it be vegetarian?
That's a great question. I think animals like we are doing here on Earth, imagine cows and things like that, that would be incredibly inefficient,
Hmm.
especially at first at any kind of trip for space. They need an enormous amount of water. The energy per, I don't know, call it kilogram that you have to put in is enormous. That's one of the reasons why that sort of agriculture is a huge contribution to the greenhouse effect too. So,
Methane.
yeah, so there's a lot of negatives I think for that, and so to me that is not a very realistic uh, scenario. Not at first. Um, Once, let's say, you have a settlement established on Mars, even fairly small, once you can create bigger spaces, you can imagine flying, let's say, embryos or something over there, and then um, having them born on Mars, so to speak, and then you could perhaps do that. But if that's energetically efficient enough, I'm not sure. There are people that have, of course, researched other sources of protein because that's very often what we talk about. And apparently, things like insects are much better, much more efficient in producing protein per energy put in, so to speak.
Mm.
Now, whether or not astronauts would enjoy eating that, I don't know. But maybe we can have a protein 3D printer that makes steaks made out of
Yeah.
insect protein or something, right? So there's a lot of innovation going on in that area, and so I think we can probably find a way to do that efficiently.
Yeah, I was gonna say that there's lab grown steaks now from the stem cells of animals. So maybe
Well, that could be another approach. Yeah, yeah. I think there's some innovative solutions there that would require us or allow us to not bring the whole animals with us, basically.
I have a question here that is asking about remote sensing. Um, so remote. You're probably sorry. I just have to clarify. You know what remote sensing is? Could you better define it for me? Is it essentially just pointing a telescope and just looking at what we get back?
Well, remote sensing is literally what the word's sensing
Oh,
from a distance, right? And
okay.
so there could be a satellite that has some sort of an antenna, and it could be any kind of wavelength, basically. And so there's active and passive sensing. So
Okay.
passive means you just look at reflected light from the sun, essentially. And active sensing would be you have some sort of source, light source or radio source or whatever, and you then look at how it reflects back, basically, right? And so you interpret the reflection either from the sunlight or from um, your active source, could be radar or something like that.
To help me better understand this question, it's asking about about improvements in remote sensing. How necessary are improvements in sensing for Mars colonization? So I assume what they're asking is how much better does a remote sensing currently need to be before we can, because right now whenever we pick Mars missions, we spend a year deliberating where the Mars 2020 rover is going to land. So I can imagine the deliberation taking a decade or more for a proper Mars colony.
Again, the question here is when do you have enough information to make a decision? right? So
Right.
if, let's say you are an astronaut and you're going to go to Mars to settle there, right? So not to just visit and come back. That's where you land, is where you're going to live for
Mm-hmm.
however long.
I want to be damn sure it was a good place. Yeah.
Yeah. So what information would you like to have before you would pick that spot on the whole planet, right?
Right.
So
Water, building material, and it's also temperature. To see what the temperature ranges were probably for year round.
yeah, no. So there's a lot of factors here, right? So you want to be able to safely land for one, right? So you want to make sure that there's not too many huge rocks, right, where you're going to try and land. Um, and so we kind of know those kinds of things just because we have landed quite a few Mars rovers successfully on the surface, right? And so we've kind of figured out how to ask those kinds of questions. But like you were saying already, that when you land, you want to have access to water. Now, there's several different sources of water on Mars. There is a lot of water there. The question is, what kind of water would you like to process? And so you have hydrated minerals. Those are things like clay or gypsum, and those minerals have water bound in the mineral. So it's not liquid water that is
Oh.
sort of in between the grains. It's actually a part of the rock. And what you can do is you can take that mineral and then heat it up until you break that bond, and then the water comes out of the mineral. That's actually what we do on Earth to make drywall,
Oh.
because gypsum here on Earth is the same thing as on Mars. It's a hydrated mineral. It's 20% water by weight. And so what you can do is you can dig up that mineral and you heat it up, the water comes off. And on Earth, what we do is we mix that water back in into gypsum, and then let it harden again, and then you have drywall.
Hmm.
Now, on Mars, you could, and that's one thing that we've done here at Michigan Tech, is that you can actually grind up that gypsum in powder, heat it up, and then just extract the water and discard the dry gypsum, and then you can keep the water basically. And maybe for future construction purposes, now you have also basically gypsum powder that you could use. But the water itself could be a source for drinking water or making rocket propellant.
So I can envision a situation where water is where for whatever reason water is an emergency resource. Like we're concerned we're not going to have enough water until the next resupply, but we also need water for rocket fuel because there's a station in orbit of Mars. Because I imagine if we have a settlement on Mars, we have a station in orbit. And they can get supplies down, but it's the margins are so tight where it's like, do we have enough rocket fuel? Like, do we synthesize more hydrogen out of the water, or do we use the water to survive until they can get a rocket down to us?
Yeah, and so being able to create your own water is a huge risk reduction for any mission, partially because it can help you keep alive, but it can also help you get off the planet again if you needed to. Right? It's by making rocket propellant. And so, right, so of course the other sources are a little easier in a way, where buried glaciers or something like that, where you can drill down and melt the glacier and suck up the molten water basically. It's another project that we've worked on here. So there's a bunch of different sources of water, but they're obviously not everywhere, and so you're picking a location is very important. So water is the number one thing. But let's say I want to also make habitats later, make underground spaces or whatever, and I want to create some other material out of a metal. So I need to have also a resource that I can then extract that metal from. And Mars is a lot more geologically diverse than the moon, and so there is a huge difference, locally, as far as what the material and the minerals are that you can get. And so you have to make sure that within your traversing range, you can find that resource that you want besides the water. Right? You don't want to travel 2,000 miles to get your iron ore or something like that.
Right.
Right? So that's fine for 10 people, but not if you want to have 1 million people.
We'll be right back. We just wanted to thank all our listeners, and especially our supporters. Without you, this would not be possible. If you want to support us, you can do so just by following and sharing us on social media. Coming up is our community question. If you want the chance to have your question featured, just tweet at HumanityXBeyond. Sorry, it looks like we already covered this. It was asking about how difficult water is to get out of regolith. I assume Martian and lunar regolith, and I assume the two are very different, or maybe they're not.
Well, no, they are very different actually, because the moon never had any flowing water basically. So you don't have the clays. You don't have any minerals there that formed because of water, like gypsum. Like gypsum requires the evaporation of large lakes or something like that, and that never happened on the moon. So you cannot find those kinds of minerals. Those minerals are typically called evaporites because they have to evaporate a lake to form, basically, or a sea. And so those things, those situations did happen on Mars. And so you can find clays and evaporites and all sorts of other minerals that do not exist on the moon at all. And so the moon has a more, let's call it, original base set of minerals. And then all the other minerals come from those base sets by weathering and water solution and stuff like that. So when you go to the moon, we have a certain base set of minerals that we can extract the oxygen from, because the oxygen is bound also in the minerals, and you can also take it off, but it comes off at much higher temperatures. When you talk about extracting oxygen from regolith, then you need to do that at very high temperatures, up to, sometimes melting the regolith. And so we're talking 1200, 1400 degrees Celsius, that sort of thing. But on Mars, that's very different. Because of those water-bearing minerals, those you only have to heat to, let's say, 200 degrees Celsius or 400 degrees Celsius to get the water off. And that does require far less energy than doing that on the moon, unless you, of course, in both places find ice, right? If you can find the ice, then, of course, then it is fairly easy to heat it up and then collect the water vapor that comes off. That's much easier compared to, or I should say easier. It is much energetically more efficient than if you tried to get it out of the minerals, basically. It's not necessarily easier to do.
I can imagine that's something I didn't think about, is the difficulty of removing the heat, because if you're melting the regolith at 1400 degrees, the amount of radiators you would need is ridiculous.
Well, but you don't necessarily want to get rid of the heat, because you would like to recycle it, right? Because if you get
Oh,
rid of it, then the next batch you'd have to heat from scratch, basically, right? So if you
oh,
can
I see.
recycle some of that heat, that'd be pretty efficient. Now, of course, when you have a habitat and humans live there, you do have to get rid of the heat, otherwise we'd slowly boil ourselves, which is bad. But for an industrial process like that, it's actually efficient to have a vacuum system in a way, because you can contain the heat, and thus you don't waste as much energy, basically.
Is it technically easier to mine regolith than it would be just like an open pit mine on Earth, just excavating?
Well, I think the excavation process is in many ways similar, except that you have a lot less gravity,
Oh
and
yeah, nice.
that means that the big scoop you want to make on Earth, you can do that by making the machine heavier, but that same machine can only take a smaller scoop on the moon because it's a lot lighter, basically. And so that's a tricky piece that people have been trying to solve. Like, how can you make a scoop so efficient that you can do it with a small robot, but you can still move a lot of material, basically.
Conveyor belt?
Well, yeah. So a bucket ladder. So you put buckets on that conveyor belt. That's essentially what people have come up with, where you get really a lot of small scoops as opposed to one big scoop, and that is much more efficient, and it produces a large amount of material, actually. So.
I understand that we gave you a prepared list of questions, and I'm sorry if I've deviated from that from a little bit, but now I'm really going to deviate from it if you'll allow me to. A very motivated youth, let's put it that way, who had some really out there questions, and if so, one of his questions was how does the media at large misportray near future uh, in situ research utilization? So what is the media like saying is going to happen too soon? I assume is what they're asking.
Oh well, that's a very broad question. So um, I think that the trips to the lunar surface and to Mars are going to happen relatively soon. I think it's going to be quite a bit longer before we have a lot of people being able to go and live there. I think there's going to be quite a bit of time between those two, much longer than people will realize. I mean, it will go fairly quick once people put enough resources behind it, but I think it's going to take quite a bit of time to learn how to do that properly. And I think that's really the key. Like you said, we're reinventing not the industrial age per se, but we're trying to do things that we're very familiar here. We're trying to do the same kind of things, but in a very different environment where the same processes that we are used to here do not work. And that means we have to reinvent new processes. And we're going to make mistakes along the way that, we think something's going to work, but they're not. And it takes time to reiterate on those kinds of mistakes. And particularly if you talk about doing things at scale, right, where now you got to do it for a lot of people. And despite the fact that we can make quick progress, I still think it's going to take multi-year iterations before we can do things. I mean, even if you think about going to Mars, right? So we go every 2 years. And so an iteration takes at least 2 years, basically. And I think we're going to have to try quite a few different things because there's quite a few things we simply cannot practice here on Earth. You really have to do it there and learn and understand how to do the processes there. Once we've done them there, we can probably better mimic them here as well. But right now, we just don't know how to properly mimic them here because we've never done it over there. And so we're using physics and other kinds of ways to predict what's going to happen. But at some point, there's you just cannot substitute doing it there with simulating it here, basically. And given the multi-year, travel times and stuff, it's going to take 2 to 5 years for every iteration, major iteration. Okay, we can do lots of small ones. If you look at how SpaceX is doing their, iterations of the starships, for instance, you can build multiple versions simultaneously and speed up that process. But that costs a lot of money. But more importantly, you need the resources. And what I mean with resources is material. You need to have people that can weld and do all these kinds of things. And of course, you have to have the materials themselves handy. And so on Mars, we're, especially at the beginning, going to be very resource constrained. And that's going to just mean that we can only make small incremental progress at doing these kinds of things. We can learn there, but we won't be able to implement things immediately right there because we don't have all the resources there. So we have to bring them, and that's going to take time. The other thing I think is people are talking very much about things like exponential growth. And I do think that growth can be exponential and very fast, but I do think people underestimate how long change actually takes. As you know, it's now 2020 and we were supposed to have flying cars and all that sort of stuff. And, some things happen fairly quickly, such as the adoption of the iPhone, for instance, or cell phones. So now I don't know what the percentage is on Earth, how many people have one, but nobody's got a flying car, right? And so some things happen faster than predicted and other things happen a lot slower. And so I think when you talk about settlement and being able to become self-sufficient, I mean, I think we're talking, like century range. We're not talking about 10 years. That's just going to take a lot of time because you need a lot of pieces of that supply chain in place before you can do these things at scale.
And speaking of those 10 years, actually, this goes well into his next question, which was what breakthrough field, like say a new individual who's like, I'm interested in this field, I want to contribute to this happening as quickly as possible. What's up in the next 5-10 years? Like something that maybe is not available now, but in 5 to 10 years, like when I do graduate, I should go into.
Oh, that's a great question. I think there's many fields that are going to contribute to this. I think there's pretty much room for any field, to contribute to this particular endeavor. I'm very working on developing the machineries that are going to be able to do these kinds of operations, because one of the things that I've always found is that people have these great PowerPoint slides, like the picture you have as a background, and it's like, oh, this is wonderful. We have these amazing structures, and that's awesome, but nobody's ever thinking about how do you actually create these kinds of things, in the sense that what kind of supply chain do you need to be able to make big starships and big cities and things like that? So you have to have mining, you need to have processing, right? And you need to have energy. That's another really, really underestimated piece here. Everything we're talking about is energy dependent. And energy really is everything. On Earth, we don't really think about it because energy is cheap and abundant. And it can be in space, but it requires a lot of infrastructure to be built first, whether that's solar panels or nuclear reactors or whatever kind of energy source we can do there. But here, I can chop off a tree basically and burn it, right? And so, in that sense, energy for cooking is easy to get. But on the moon and on Mars, I can never do that. There is no tree I can just chop out. There's nothing I can just pick up and burn. So how do I do that? I need to have a much more elaborate supply chain before I can actually make a meal, right? And much, much more difficult than here. And so it takes quite a while for that basic infrastructure to be developed there. And it also means that we're always going to be dependent on that being artificially created, basically, by us. And before that is in place, that's going to take a long time. So what do you need to contribute to? Well, first of all, we need to develop those machines to do the dirty work, to dig, to extract, and get the stuff that we need to do, whether that's metals or oxygen or fertilizer or anything like that. And that's the first basic step. Then you have your raw materials. And then you're going to need to have the manufacturing facilities. Okay, once you have the raw materials, now you need to make something from that, whether that is those pressure vessels, right, for living, or making, expanding greenhouses, or whatever it is that you want to achieve. You need to be able to use the local materials to produce more of them. That's when you start becoming more self-sufficient. When you can start to grow, that's when you start to become independent to a certain extent. Right, because you can make more food than you need, right? That means you can now start to grow your population. And if you have now more energy, because you need to be able to somehow grow your energy as well, energy production. So once you can start growing your energy production, you can start growing other things. And so those basic needs, those basic building blocks have to be in place before you can start doing all these other things. And that's where the next 5-10 years are really going to be crucial, is to develop those technologies, the robotic excavators and miners, and the processing facilities to take that mined material and then make something with it, right? And then when we build our first landing pad, our first house, our first whatever, that's when we really start to learn and understand, okay, now we can start to grow, because now we know we need to build a lot of these kinds of machines, and then we can grow a lot in that area. That's going to be the key piece. And so basic stuff, in a way, the next 10 years are going to be fairly basic. Figuring out how to set that supply chain in place. Once that supply chain is in place, a lot is going to be possible.
The last question is, I'm going to read it directly. What major technical barriers need to be crossed before we can carry out effective scalable, italicized, scalable ISRU on other celestial bodies?
So what technical problems are you talking about?
Yeah.
So I think the key part for being able to successfully do any ISRU on any kind of body is to really figure out the industrial nature of that system. And right now, NASA and anybody who's done any space exploration, we've only really done, science-based stuff, which by the way is great, but it's not intended to do hardcore sort of mining work and do that for many years without supervision and without maintenance. Right, so look at the Mars rover, the wheels, they were breaking, right? And so that's just driving on a surface. Now, it has driven less than the distance of a marathon. So if I have a mining rover and it needs to go back and forth, it would drive, 2,000 kilometers. So, 50 times more. And it would do it much faster. it would have to carry a much heavier load. And, all of these kinds of factors mean that you have to design a completely different type of robot to be able to do that. And I don't think we figured out how to do that yet. And so any kind of mining operation, even here on Earth, maintenance and wear and tear are huge costly issues that cost literally billions of dollars in the mining industry here, because the wear and tear leads to shutdowns and equipment that breaks down in a random spot where now it's blocking the access and the mine has to be shut down. And so if that happens in space, oh yeah, no, my nearest AAA call or whatever, right? So my nearest repair shop can't get there until next year, or you just have to send a whole new vehicle. And so I think there's a lot of work to be done before we can do any significantly scaled mining operations in making those systems durable. And it's not just the mining, it's also the processing systems and all these different pieces. Because you can't just say, oh, hey guys, I need to call in the repair shop to just drive by and fix my truck on the road, right? So that doesn't work. You can't do that on the moon or on Mars or an asteroid. So how are you going to how do you make systems that can withstand kind of abuse, if you will, from mining?
That's your entire field of work right now, is figuring that out, right?
Well, that's kind of what I'm focusing on, but I'm focusing on it because it is very important, and it's not glamorous. It is not sexy aerospace, cool, sleek satellites. No, it's grubbing in the dirt and in the rock, and then you gotta make sure that it works under any condition, basically. And that's aerospace engineers do not know how to do that. They want class 100,000 clean room, and we got no dust particles or whatsoever. But when you talk about mining, that's simply not an option. Your vehicle is going to be in the rocks, in the dirt, and you're going to figure out that we didn't design it strong enough. It broke. Okay, what are you going to do now? So there's a lot of things that need to be figured out, how to do these kinds of things and make them last. Because astronauts can't just go there and then replace a wheel or whatever. You're going to have to figure out how to remotely repair it, perhaps self-repair it, maybe by other robots. There's a variety of different ways you could go with that. But the idea is to make things robust for many years, make them work, make them last. And that's a very different kind of design than we've ever done. Basically, we've never done this before.
Yeah, I was gonna say the closest thing we've had to a manned rover is the lunar rover, but that it was cut down on weight and it had to run at most 3 days. So
Well, yeah, and so none of the systems we've designed, even though they lasted long, all right. So the Mars rovers have functioned for like 10 years, so they've lasted long. But that's kind of to a certain extent saying, look, my car has been sitting in my garage for 10 years and it still works. That's right, but it hasn't been working very hard. And so the wear on the systems is very different than if you daily drive 100 miles. So you different parts wear out, and you get a very different kind of problems to deal with when you design for systems like that.
well, I would like to argue with you on the point that your job is actually glamorous, because if you design the equivalent of the Ford pickup truck, I think is sort of what we're describing, a vehicle that can take a beating and that can work, very difficult every day. If you design that vehicle and the first future Martian colonists end up relying on it to live, like if they rely for transportation, if they rely to carry cargo and everything, that you're going to become glamorous and famous very quickly for designing that vehicle.
Oh yeah, I mean, I'm sure there is some, to a certain extent, if you look at the market in a way would decide what works because it doesn't break, right? So that's the one they're going to go with, because you can depend on that one, right? So your life is not in danger in a way, and that is great. That would be really good. But I guess what I'm saying is it's not like designing a Formula One race car, right? It's not that kind of glamorous. It's not like designing the Concorde airplane, right? It's designing the Boeing 747. You know what I mean?
Yeah.
Which it's Queen of the Sky kind of thing. But it's a workhorse in a way, right? It's of course glamorous because it works very well. It is a very well-made machine, which in itself has its own rewards and is glamorous in a way. But it's like geotechnical work here on Earth. It's very underappreciated because it's underground and nobody sees it.
Right.
But if it wouldn't work well, we would all have huge problems because we wouldn't have clean water, our houses would break, and our streets would crack and all that sort of stuff. And so there's a whole bunch of things that are not glamorous but very important. It's like Mike Rowe, his work show, right? That's the kind of jobs that we're talking about here. It needs to be done. It's not I don't like to use the word sexy, but it's not glamorous.
Glamorous, yeah. Well, I'll let you go to sleep because I could talk on this topic for hours, but I understand that you have your life to get back to.
Oh yeah, no, it's okay. I can talk about this for days myself, so it's great to talk to you.